replace your skin cells at a higher rate? Well, we replace them faster and faster and faster. What happens to your skin?
It starts aging.
Ages quicker. This is literally a problem. Now, we can solve that problem. We can solve it with telomerase. So telomerase just makes telomeres. They make long chains at the end of the chromosome, so we can elongate the chromosomes. Is there a problem with that?
Yes.
What do you think the problem with that is?
It allows unlimited division.
Excellent. Now you have cancer. So there's fine-tuning this, right? Certain cells in your bodies have this ability, but those are the ones that are more likely to experience this problem. All right, so let's go through and finish up this worksheet together, because hopefully we're at about this point. So we've done this replication bubble a lot. So the arrows represent 3 prime, so that's 3 prime. That's 3, that's 5. So that's our point of initiation. Helicases are going like that. What is this called?
An Okazaki fragment?
Excellent. It's Okazaki fragment because that's the lagging strand. So therefore, we're going to have the same problem over here. And these are called our leading strands. Okay? As the forks come together, what happens?
I'm sorry, what forks?
As the forks, these are called replication bubbles or replication forks. As they come together, what happens?
The bubbles merge.
Excellent. Bubbles merge. What enzyme merges them?
Helicase?
Not helicase. Helicase opens things. What merges?
Ligase?
Ligase. Nice job.
Yes, I was right. Okay. That's crazy.
Okay. So, on planet Mandoid, DNA polymerase 3s as nucleotides onto the 3' end of a growing nucleic acid, just like on Earth. However, on Mandoid, DNA polymerase can only start a new DNA strand on its own. It does not need an existing 3' to do. What is that going to do? What do we need to get? What can we get rid of?
Lagging strands?
We get rid of the lagging strands. Excellent. So we don't need primase because we can start it. It does not need an existing 3'.
You cannot hear me.
So what then can we get rid of? Primase. We don't need primase anymore. Excellent. And if we don't have primase, what don't we need to do? We don't have to replace. Yeah, excellent, Jane. We don't have to replace the RNA, so we can get rid of DNA polymerase 1. So you still need to be able to ligate them together because those replication forks are still going to come together. You still need helicase to unzip everything, but we don't need those other two things. Prokaryotes do not have linear chromosomes. They have circular chromosomes. And they only have one, and they're very, very, very tiny, okay? They're like 1/50th, 1/20th to 1/50th in size. How many points of initiation do you need?
Probably about half that.
Well, no, so if you're only 1/20th or 1/50th as big, how many initiation points do you need? 1/20th or 1/50th. So if you have 20 initiation points typically on a eukaryotic cell, you only have one. That's exactly what happens. So a eukaryotic, long, giant strands, I mean, we're talking hundreds of millions of nucleotides long. But a prokaryotic is tiny, itty little bitty circular chromosome. So if you're circular too, if you start at this point, by rule, you're going to end up at the exact end anyways. I don't have to go in either direction. I can just go in one direction. What makes it really easy. How do we feel about this page?
Not too strong.
Not too strong. Okay, Mar, what's going on?
I guess it went a little too fast for me, like talking about the about the prokaryotes. Those are circular